Thanks for coming, everybody. My name is Johnson Lindblom. I'm a senior math and finance major. Today I'll be talking about a research project I've been doing. It's been applying Bayesian methods to model the spread of COVID-19 in Texas. So first I'm going to talk about some of the theoretical background behind the models that I've been building. When you try to model something like COVID-19, one of the most common frameworks that people use is what's called the compartmental model. So the idea behind these models is you try to dissect the population into a set of bins and then model the transitions between individuals in these bins. So here we have the SIR model. SIR stands for susceptible, infectious, recovered, because there's three bits. You then have a system of ordinary differential equations that models the transitions between the individuals in the bin. These equations are governed by two parameters. You have beta and gamma. Beta represents how quickly are the infectious infecting the susceptibles, whereas gamma reflects how quickly are the infectious recovering from the virus. So you can then solve these equations numerically to produce a plot like this one on the right. So in this case, beta and gamma are such that there's a single peak. But you can imagine that if beta is much bigger and gamma was much smaller, that potentially everybody could become infected. Whereas if the reverse was true, so beta was smaller and gamma was larger, barely anybody could be infected at all. So depending on what these values of beta and gamma are, you can have a very different picture. So what's important is figuring out, okay, well, what should these values be when you're trying to predict something like COVID-19? So now I'll give an eagle-eye view of the Bayesian formalism that I use in my models. The idea is that you have some probabilistic model for the data that you observe. And so in my case, I've limited myself to looking at just the daily new numbers of COVID-19 each day. And so the model is going to depend on some parameters. We're going to collect all these parameters into a vector theta, and then using Bayes formula, you can write out the formula for the probability density function as P of theta given D, which is the data, equals P of D given theta times P of theta divided by P of D. And so this is a formula for the density function for the posterior distribution given the data. This will require us, though, to specify prior distributions over the model parameters before we see the data. So in advance of observing any data at all, we need to have some kind of idea of what are the relative values of all these parameters. We then use computational methods such as Markov chain and Monte Carlo and its various flavors thereof to then approximate this P of theta given D. Here's an example of what I mean by putting probability distributions over the model parameters. So here we have two different forecasts for the total cumulative deaths in Texas due to COVID-19. Here we have two median lines for the forecast, but then we also have a range that we think with 95% certainty the cumulative deaths will lie in this range. So here's kind of the goal of my project. It was to learn how to do this kind of forecasting. So even if you were to use MCMC for parameter inference, there's still a pretty serious problem with just the basic SR model, and that's that the parameters are fixed for all of time. So if you were just to go fit a basic model to data, you'll see that it fits pretty miserably and it's not very predictive, especially if you compare to actual data looking forward. So the reason for that is you can just think of it intuitively. As a nation, we're entering into our third big wave of upticks in daily COVID-19 cases. So and the reason for this is because there's been a change in the spreading rate itself over time. So a change in the beta parameter. So this research group out of Germany, they noticed this pretty early on, and the way that they overcame this was they developed a change point model. So what I mean by change point is at key points in time, so discrete number of points in time, you're going to allow for the parameter value to change. And they kind of targeted these around the points of government intervention. So in Germany, there were three major interventions that were taking place. And so what they do is they say, okay, let's run the algorithm three different times. One where we don't allow it to change at all, which is the red curve. A second time where they allow for two single change point. So this is the orange curve, and then a third time the green curve. And so what this lets you do is adaptively change the spreading rate in time to model the effects of different interventions or changes in human activity. So if you live in Dallas County, you're probably pretty familiar with Judge Clay Jenkins' shutdown order back in mid-March. So one thing you might be interested in is, okay, what were the effects of that order? So here's a model that's trained up until April 13th. So in my model, the number that you really care about is the effective growth rate. And so what the effective growth rate is it's just the growth rate of COVID, so the rate at which COVID is being spread, lambda, minus the rate at which people are recovering from the virus, mu. So if this number is positive, then you're in trouble. So if this is above the dashed line, that's bad. That means you're having an increase in daily cases in time. Whereas if the number becomes negative, then it's a good thing. That means that your daily cases are are decreasing on average. So in this model, you can see how we have three different kind of regions on all of these plots. What the regions indicate is a 50%, a 70%, sorry, a 50%, a 75%, and a 95% credible interval over the values of the parameters or the values at that time. So here I'm tracking the effective growth rate in time, and I'm saying here is the range that it is likely in with the relative probabilities, which is the key point. This is the important, going back to the Bayesian framework. This is what the Bayesian framework allows us to do. And the reason that's important is because here you can get drastically different forecasts very far out into the future, even if this value changes very almost insignificantly. So yeah, so moving on, we have some plots of the daily reported cases that we would expect given the model, as well as the total reported, so the cumulative people affected by the virus. And so one thing to keep in mind is that uh, the change points, you don't know when the change points are going to occur. After the fact, you can figure out, okay, they likely change around here, but looking forward, you don't know when they could occur, unless you do, but that's an edge case. So here's an example moving a little bit more forward of to up until June 1st. So training the model up until June 1st. So we still have that same change point back from March, but now we have another spike right around the time that Dallas's county the lockdown was lifted, and then we have a dip and then another spike. So it's not as clear as to what caused the dip and also the spike. If you have ideas, I'd love to hear them. But so the kind of the MO of this process is that you can then do it for all of time and see how did this effective reproductive number change throughout the entire history of the virus. So here's the latest model. It is trained with a weekly change point starting May 31st, but before then, I'm just using the change points that I mentioned before, the one in March due to the shutdown, the one after the Dallas lockdown lift, as well as the two that I'm not quite sure why they occurred. So here's kind of the second half of the story for the change points that happened between June up until now. We really had three major ones. So right around Memorial Day, we saw a big uptick in the effective growth rate and in the daily cases. Right after that, we had the Dallas County mask mandate, which, whether it was that or due to something else, a lot of these trying to attribute what the change point was is kind of tricky. It could be due to a host or even a combination of different factors. So right around then, though, is when we had the Dallas County mask mandate, and the effective growth rate decreased back negative. But then since then, we've seen it increase a little, decrease a little, and increase again. Up until present, as of present day, we are positive again. So a lot of that could be due to schools reopening, COVID fatigue, like Judge Clay Jenkins talked about, things like that. So I guess like the message for that I tell all of you guys is that we're positive now, and we need to go back negative if things are going to get better. So this plot on the bottom is just trying to give you an idea of the fit to the model to the actual data in time. There's two big kind of outliers, and what those were was what I mentioned earlier in the presentation, where Dallas County reported huge numbers in consecutive days of this backlog cases. And these were cases that hadn't been reported, they were back from like June or July. So, and that's kind of the benefit of using the student t distribution in the model rather than just like a normal distribution, is that the model isn't as sensitive to these huge outliers. This is a little bit offset from the date of this presentation, but here's my 4-week Dallas County daily new COVID projections starting on October 14th. So the way that you interpret this kind of a prediction is, so say our date of interest is November 1st. So the darkest green shaded region is the 50% credible interval. So what this is saying is, so the credible interval starts a little bit before 600 cases and ends right before 800 cases. So the statement I would make is, on November 1st, the daily new COVID cases we will see is with 50% probability is going to lie between 600 and 800 cases. Now you can continue to make similar statements with the other credible intervals or at other days, right? So I'd say with 95% probability that the daily new COVID cases we will see on November 1st will lie between 400 cases or about 1,100 cases. In the interest of time, I'm just going to give a brief overview of the rest of my project. So here I have a model for Texas, which I made using the exact same approach I've described the rest of the presentation for Dallas County. So kind of the goal of my project is to carry out this analysis for Texas as a state, but also the other 9 largest counties in the state of Texas alongside Dallas, and try to gauge, okay, what change points are similar in terms of timing and in terms of magnitude, and what change points are different. To kind of paint a picture of the story of the spread of COVID in Texas, and see what kind of variations in terms of policy and whatnot, and try to gauge, what interventions were taken in some counties or weren't taken in some other counties in terms of timing and in terms of kind of severity, and try to see, okay, well, what worked and what didn't. So that's kind of where my project is headed, and I'm still working on the rest of this analysis. The key point I'd like everybody to take away from my presentation is that we really can affect the spreading rate of COVID. It's not just something that just fluctuates randomly and we can't really do anything about it. We definitely can, and we can measure the impacts of the interventions we have done. So, the most recent uptick in the effective spreading rate, which I showed earlier, Judge Clay Jenkins is attributing that to people having mistaken beliefs on reopening and COVID fatigue. So I just really encourage everybody to, stay strong, keep wearing masks, don't fall victim to COVID fatigue, and hopefully we can get this effective spreading rate to be back negative. And as a last note, I thought I'd show the model that I built for COVID cases here at SMU. Just to connect the dots, if you've seen this dashboard here on the right, hi, that's my dashboard. I know a lot of people have seen it. So in terms of SMU's change points, we've really only seen one change point throughout the entire semester. It happened right around September 23rd. So there's a couple, I won't really speculate too much really as to what caused it. I know right before then was the peak quarantine numbers of students self-quarantining. But yeah, so my model's currently predicting that hopefully it's accurate, that, we're just going to kind of tip her off to the rest of the semester. At the worst case, we're going to see it just kind of oscillate at some constant level until we really just kind of all go home for the break. But yeah. I'd like to thank Dr. Alejandro Aceves and Sabrina Hetzel. We formed a COVID modeling group back when the pandemic first struck, and we just kind of been bouncing ideas off each other ever since and talking about modeling, mathematical modeling of the pandemic. I'd also like to thank Dr. Matthew Parno from Dartmouth. He was one of my advisors over the summer on another project, but he introduced me to the Markov chain Monte Carlo kind of Bayesian approach to inverse problems, so I'm grateful to him. Also, thanks to the Priceman Group for sharing their code on GitHub that allowed me to do all this much quicker than I could have by hand. And also to the Hamilton Scholars Program and the Office of Engaged Learning for their continued support of just all the research that I've been involved with here at SMU.